show you that the evaluation of the boundary of the constructed object, object constructed through a combination of the simple shapes, is not that involved, and that you can do this in a straightforward way. And we were able to actually write a formula, as it were, or an algorithm, right, which will allow you to list the boundary of a combination. So, for example, here, if you want to find the difference of the two objects, example objects that we started with, then applying this formula will give us the right boundary model. We then saw how we can, compute these components that we have listed in the solution, right? And that is through this realms of set membership classification. And again, we did not do all possible set membership classifications, but just enough to convince you that this is something that can be done through an algorithm or a program, right? So, for example, an edge with respect to a polygon, right? Or I think somewhere we had done this point with respect to a polygon, right? So in both these cases, the attempt is just to show that while boundary A outside B, or a set membership classification of X with respect to S seems very abstract, it turns out that there is a formal procedure that can be used to basically split X into these parts. And that's what we did here, right, in this example, without actually looking at the details. But the details for this particular case, we went through as to how we do intersection and then basically toggle at every intersection point, right? So I come to the first intersection point, I switch the classification. From out it goes to in, then it goes to out, then in, and then out again. And then we saw one counter example where the third possibility in the set membership classification, right, the classification of on, right, where the boundary element of one is on the boundary of the other, right, as in this case, these two segments that are drawn here, right, they are the what we call as the on case. So when I classify this edge with respect to the solid B, I will get this to be out and this to be on, this to be in, and then that's it, right? And so what this does for us is that while in the regular Boolean algebra that you might have learned in school, right, with the sets of discrete items, the on case is not a major problem at all, right? In fact, we don't even handle that separately. But when we are dealing with point sets where the boundary becomes important, that we want it to be a closed bound set, right? We cannot leave this hanging like this. So for example, in these results, right, if we apply just the classic set theoretic approach, we have these dangling areas where there is no closure. And so to close that, we now have to add an additional term to ensure that we have the right boundary. And then that gives us the correct final formula, right, where this valid is something that depends on the operator being used. And we saw that that is purely dependent on the orientation of the boundary element. If it is an edge, it is the direction of traversal. And if it is a face, it is the direction of the normal. And by looking at the relationship between the normals of the overlapping faces or traversal directions of the overlapping edges, we can conclude whether it is to be included in a union or a difference or intersection, right? And that's what is listed out here, right? And that gives you the complete solution. Okay. Then I had a quick attempt to try and sort of sketch for you how the 3D case would work with just the kind of computations that I had described for you, namely edge with respect to a face or a solid, right? And I hope I was able to show you that we can, just by starting with the edges of one object, classify the faces of the object completely with respect to another solid, as we did here, right? And then it's only a question of assembling those faces which are in or out, depending on the formula of the Boolean operator that we are interested in, and get the right result. This is a slightly high-level view of the problem. There are some cases that we have not addressed here. But as I said, the point here is not to give you the details, but rather show you that it is indeed possible in a closed form sense. Sorry. Again, I'm trying to get that ribbon at the bottom. That is something. Yeah, here. Okay. So that's essentially where we stopped. So let me just pause here for a minute and check if any of you have any questions or comments or doubts in everything that we have done so far. Sir, any questions? Yes, please.
So in these cases, we talked about whether these faces are overlapping. So what if an edge is being overlapped or one point is overlapped?
Okay, so I don't know if you recall. I mean, are you asking how you will find whether they are overlapping, or what do you do when they are overlapping?
No, sir, in the same equation type, like we regularize this operator in this case.
Yeah.
Representation.
Yes. Please ask the question again.
So in these cases, we talked about when surface is being overlapped. So we get this valid B A on B.
Yes.
So
yes.
What if it is a point or an edge? Just one edge.
Fine. So let me deal with the edge first, because we already have an example for that, which is here, right? In this case, right? For this example, right? These two edges are the overlapping cases, right? This is a portion of the boundary of the blue set, the orange set here, which lies on the green one, and the same for the green one that lies on the orange one. So as you can see here, right? This portion of the edge lies on the boundary of the other, and this portion of the edge on A lies on B. Okay, so this is one such possibility. And here what we do, as I said, is that you look at the direction of traversal of the same portion of that edge in both the objects. So the blue here shows the direction of traversal in the L, and the orange here shows the direction of traversal in the rectangle, right? And now, depending on these two directions, whether they are parallel or anti-parallel, we will choose them to be part of union or difference or intersection. Okay, so that's for edge overlapping an edge. Now, I'm assuming that your question is what happens if I have points overlapping an edge, right? That's the question you're asking.
Yes, sir.
So let me just draw this object again on the side here. I have the L in orange, and I have the rectangle in green, right? So now your point is right, that these vertices, right, respective vertices, lie on the other object, boundary of the other object, correct? So this point on the orange also lies on the boundary of the green object. So what do we do with these is the question you are asking. I want to go back here and highlight these two conditions that we listed. Right? We said that set membership classification has to satisfy two conditions. One, the set being classified must be lower dimensional than or equal to the set that is being classified. In our case, we are classifying an edge with respect to a face, right? So this is okay. This is order dimensionality 1. This is dimensionality 2. So this is what first condition is okay. The second condition says that the dimensionality of the result must be the same as that of the set being classified X. What does that mean? Which means that every element that you get as a result, X out S, X in S, all these sets, right? they must be an entity that is the same dimensionality of x, which means it must be an edge. So here, while you are right that this point on the boundary of B lies on the boundary of A is correct, but the dimensionality of the point is 0, whereas the set I'm classifying is actually boundary of A, which are edges, which is of dimensionality 1. Therefore, these will not be used in the result at all. They will not be taken up as a result of the set membership classification. Okay, and so we don't have to worry about this.
Okay, sir. Thank you, sir.
You know, because of the second condition. Any other question? So the same thing in 3D, right? If I have an object like this, and perhaps another object that sort of, let me pick another color. Another object that sort of overlaps with this edge and this edge, and then, you know, sort of comes here, right? Then same thing applies. So I'll use it in color. So there is an overlapping vertex here, 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 and that's it. Those 4 vertices are overlapping, and these edges are lying on the boundary of things. This edge and this edge. But they will not count at all. Why? Because I'm now classifying what is boundary of A here. Boundary of A is a face. Therefore, all my results must be in terms of face outside, portion of the face outside A, portion of the face outside B, portion of the face on A. So this will classify as an on case. This will classify as an on case, but this will not, because its dimensionality is 1, whereas we are looking for entities with dimensionality 2. Okay? Fine. Any other points?
Sir?
Yeah?
So last class I left off one question, like the G1, G0, G1 curves.
Aha, yeah. Okay, so just tell me what he said about this. I wanted to see that notes, but I couldn't see the recording. My mistake. Hang on. Let me just open up the screen here. Yeah, so what was the point he was mentioning? Just say it again and I will try to.
Sir, he didn't actually mention the point. Like he showed that these are the G0, G1 curves that must be chosen with respect to the company. Like each company will have their respective G0, G1 grades for filleting, etc.
Okay, hang on. I think maybe L8 is where the continuity, or maybe after surface. Huh? I'm just looking for those pictures. This is the one. Yeah. So just to reiterate this again, right? We are looking, when we say continuity, essentially when you're putting 2 entities together. Okay, so you could have surface patches, right? You know, for various reasons, you may not model them as a single patch, right? You will model them as multiple patches. And then, you know, sort of continuity at the junctions becomes critical, right? And then that is where we talk about continuity, right? Because we have polynomial expressions, continuity within a single entity is never a concern at all, because we know that it will be continuous, because my representation is that like that. So the only time we worry about continuities are at junctions, right? When I have a surface meeting a surface or a curve meeting a curve, etc. Correct? So we define the continuity in terms of the derivatives, right? So the way we talk of continuity is CK, where this implies that up to the kth derivative is continuous. Okay, that's the notation. So here I have C0 continuous means that I go along the path and I will never find a gap. Right? So at the junction, the two curves touch each other. That's all is guaranteed. There is no break for you to fall through. The same thing, C1 continuous means that the first derivative is continuous, which means tangent continuity. So if I were to try and derive the tangent of this curve and plot it, I should get a continuous curve. Right? There is no break in the tangent. That's what this is showing. Likewise, it continues. C2 is second derivative, and as I said, K is the kth derivative. So it's a purely what I would call a property of the representation that you have of the curve. I compute the derivative, see if it is continuous at the junction, you are set. You may recall that we did this for the spline curve, right? Because it is defined piecewise, right? So, you know, it is defined one way in one segment and another way in another segment. But we showed that at the junction, it is always Ck minus 2 continuous, which means that if K is the order of the curve, then it's continuous up to 2 orders less derivatives than that. So if I have a cubic, so K is 4, I have C2 continuity, meaning curvature continuity is guaranteed. So again, continuity you talk of at the junction. But because, right, the vectors, the tangent vector, etc., right, they have two components. There is a magnitude and there is a direction. Right? And when I talk of C0 continuity, I assume that both are held constant. Okay. Whereas in the CAD sense, in the CAD modeling community, we define another type of continuity where I only get visual continuity, as it were, meaning the direction of the tangent vector looks the same. So you can look at this curve here, and if this was the junction, you will say that it has got tangent continuity. Even though if you were to compute the tangent, you know, using the algebra, then you will find that the derivatives are not the same in magnitude, but they have the same direction. What this does is that it gives you some flexibility in terms of designing the curves, because somebody would have designed this and you are responsible to design this, and maybe you also have a constraint at the other end like that. And so your job becomes very difficult to maintain a continuous curve with a certain shape, right? And therefore, what we do is that we allow this relaxation that as long as it is visually continuous, I don't mind, I will take G1 continuity. The same thing holds good for surfaces as well, right? So I have one surface and then, you know, I may, you know, this is continuous in visually, but we don't know about magnitude unless you compute this, right, across this junction. So CK continuity is both magnitude and direction. G continuity is visual and it is only direction. So I will, as I said, I did not go and see what he meant by that. But if I can, I will look at it and then I will. So you can see examples here, which we had done in the class. Okay. Yeah, I don't know if that clarifies your question.
Yes, sir.
Okay. So G is usually, sorry, I didn't want this here. G is usually visual, and C is both magnitude and direction. So it's the more rigorous condition that we have. Not this one.
Sir?
Yeah.
So I actually asked because when he switched the curves to G1, G0, G3, there wasn't a noticeable change, like minor change only, not the great change in between the smoothness. So that's why.
In the visually, you could not see much difference, you're saying?
Yes, sir. Like it was, I don't know, the stress analysis, the red part in the fillet area. So there wasn't much visual representation while changing it to G0, G1, etc.
Okay, that could well be a function of the curves you started with to begin with, right? I mean, if they were reasonably close, you would not see much changes when you insist on higher orders of continuity. you may not have to tweak it much, right? I mean, in the sense that if you start with something as dramatic as this and say, give me G1 continuity, you will see a very dramatic change in the curve, right? Because it has to go like that, right? But if you sort of start and, see something like that, you may not see much of a change in the two curves. I mean, I'm not sure if this is what exactly he did, but that may be one reason. That you may have been close to that order of continuity well before, so you don't see much changes.
I have the screen recording, so I can share the screen and show it if.
Okay. I mean, you have it now?
Yes, now.
Okay, let's take a look at it. Hang on. Let me just do unshare now. Yeah.
I want to connect this point to this curvature that I have created. I'll move it a little bit further again. We'll see. If you want to connect any of this, we have skin option, or there are multiple options that you can explore with. I'm using skin option for now. Like you can skin from one curvature point to the other curvature point. Basically, this looks something like this. The option here as well. Like, one of the main advantage of filleting in alias is you have so many factors to consider. You can change so many variables. Like even with the filleting option, we have G3 curvature, G2 curvature points. Let's say let's see how it works. Initially, let's consider a G2 curvature where the curvature has to be G2 when coming from this thing to this thing. Say the G2 curvature being created. If you want G3, I can do that same. Let's say one problem with I find with the alias is there is no undo option here, because there are so many. But for filleting option and other trimming options, they have an option called untrim. So basically, undo of you can untrim the previous surfaces. Good thing is you have right now I don't need, so I will delete this curvature. It should be much more smoother now. Constraint on filleting option also, because
is this G3 is he saying?
Values that each.
I'm just skipping fast. Yeah. What is it?
Is this the one that is he saying G3?
Yeah, this is where he showed, and then the temperature plot he shows after
They
that.
don't need, so once they manufacture the die or something, they'll be fixing with certain parameters in terms of curvature. So the more curvature it is, the more it will be difficult for the company to manage the other manufacturing aspects. So there are certain limits, and they'll do all the curvature points under these limits. So even with this curvature, you can see.
Is it where?
Okay. So the point, I mean, I don't know what was the confusing part. There are two parts here that he is talking about. Okay. The G2, G3 references that he is using, they are references to continuity. Okay. Meaning that if I'm looking at a property, a differential property of the surface, it could be curvature, G2, or it could be G3, which is the next level derivative, then it will be continuous. That's the G star part of it. The contour plots and the what look like the zebra plots, and they are actually called the zebra plots that he showed you, they have to do with the quality issue. Okay. Now, what I mean by that quickly, we will cover this a little bit, but let me just, you can stop this now, I think. I mean, is that the point that you're referring to?
Yes, sir.
Okay, so let me just, then go back to my screen and I will just illustrate that. What did I do? Yeah. So what we mean, two things are happening here, and he's probably showing both together, and probably that's why it is adding to the confusion. Let me just see if I can draw an example for you. Okay. So if I were to give an example, let me look at the sine curve. Okay, not exactly the sine curve, but So you know that this is C1 continuous, right? Actually, you know that it is also C2 continuous, because you compute the first derivative, it will be a smooth curve, and so forth. Right, second derivative also will be, because it will just toggle between sine and cos, and you'll get a nice continuous curve. But is it a smooth curve, right? Is something that has to do with something other than continuity. See, continuity is with respect to the derivatives, right? But whether the curvature is smooth or fair, that has to do with variation of the curvature. Even though it is smooth, if it varies too much, right, then it won't be considered as a smooth or a fair surface. So this has to do with the quality of the surface from a CAD or a application point of view. This is purely geometric, derivatives. If they are continuous, my curvature, I have whatever continuity that I'm talking about, right? But in achieving this continuity, if my curvature is varying a lot, right, then it is not a good quality surface from a CAD point of view. And one of the things that people do basically is right, for example, in the automotive space, you will see the reflected light from the surface, right? And clearly, when you have a lot of undulations on the surface, right, they may be all continuous derivatives, but there are still undulations on the surface. The pattern of light that gets reflected will be very distorted, right? And that is taken as one measure of quality. And what you saw in that alias plot, right, a contour plot of curvature as well as this zebra plot, they are actually measures of that, of quality of the surface, not continuity of the surface. Okay. So keep that in mind. Maybe we'll revisit this point when we talk about surface quality after we finish all this. And again, maybe you can raise this question there. Okay. Fine. So I hope I'm in the right file. Yeah. So we finished this, and as I said, we were talking about how the solid can be constructed, right, using the Boolean operations. So my only question that I had left with you at the end of the previous class was that instead of an object or two objects that looked like this, linear, rectilinear solids, if one of the objects, so let me say that the orange object is still the same, just to make things easy for us, except for the top surface, right, is some curved entity, and everything else is planar. And the green entity is completely curved. Okay. And now you're asked to find the Boolean operation again, which is A union B, or A minus B, whichever catches your fancy. Question to you now is that which step amongst these do you think will have to be changed? Right, I can start with this vertex, right? Find the intersection of this edge with the faces, find this intersection point, and then I can, classify this edge as out because this vertex was out, and then toggle this to in because there's an intersection point and this is out again, and therefore this segment is out and this segment is, oh, sorry, mistake, 1 second. Not thinking. Because there is no intersection point, this is vertex is also in, and there is no intersection point here, therefore the segment is also in, therefore this vertex is in, there is an intersection point here, therefore this segment is in, this segment is out, therefore this vertex is out, and therefore this segment is out. Right? I can then, use the same logic and create some edge in between these two and say that these are the two faces, and like that I do for all the faces in one object and create this thing. Okay. But what has changed between the process here and here? Is there any change at all? Can you think of anything? Look at this edge I1, I2. Right? You know that there will be an edge between I1, I2 because, as I said, you get this as an intersection between an edge and a face, an edge and the same face, and therefore this must be, a result of an intersection of this face which contains these two edges and the face which it intersects on the other object. Same thing is true here also, so it will hold. But what will not hold is that while I may know I1 and I2, I may not know the equation of I1, I2. Why? Because if it is a linear object, then two endpoints will define the line of the edge, equation of the edge. Here it is not the case, right? I know that there is an intersection edge between I1 and I2, but the equation of it will not be known to me. And to find that equation, I actually have to do intersection of this curved face S1, F1, and this curved face FA1. So unless I do this intersection, right, FA1 intersects FB1, I cannot get this. Unlike the linear case. But other than that, everything remains the same. So this is the only additional complication when you're dealing with curved objects, that while you can get the topology or the connectivity of the object, right, from this process here, the geometry will have to come from actual intersection. So now I want you to recall the issues that we talked about when we mentioned the surface-surface intersection problem. Okay. I really have to. So I'll now go to this picture here, which you have already seen. Right? Imagine this to be the bottom surface that we talked about, right? And this to be not in the middle of the surface, but at a corner of the surface. So, maybe the case that we were dealing with is something like this. Right? One object is here and another object is somewhere over there. Okay, so this is one face on one object, so FB1, and this is one face on another object, which is FA1. Okay, So remember we said that we will get points of intersection. But I cannot fit it in this space because then it will neither lie on this surface nor on this surface. So I fit it here and map it back to the surface, which means that I have one boundary of the face, the red face, which is given by the points lying here, points of intersection here, and one boundary on the blue face, which is given by the points of intersection that are in here. And therefore, when I actually form the result, right? It'll look somewhat like this. Sorry, not. Right. So it is on one surface and another surface is that, and therefore you will see this gap. Right. So this is I1, this is I2, and the intersection curve on one face looks like that. Intersection curve on the other face looks like this. So in some sense, this does not satisfy your watertight policy, right? Requirement that my object must be watertight, because now I have it is violating the condition, right? Because this edge on this face does not lie on any other face. This edge on this face does not lie on any other face, and therefore it violates your first check for validity. And so this is a problem that all CAD systems grapple with today, when you have freeform surfaces forming the boundary of the object. You have to do intersections, and even if you do curve intersections, in the case of curved entities, you have to do surface-surface intersections and get these intersection curves. But since they don't lie on the other surface, you will have this gap. So what people do is that they cheat. Okay. The way they cheat is that they create an entity called an edge, which is between these 2 points I1 and I2. Okay, that's the topology. But the geometry, right? They store two geometries. One is an equation of a curve that for the surface A, and one is an equation of the curve for the surface B. So that when they are drawing or doing this in one, they will use this equation, and when they are calculating for this face, they will use this equation. So that, from a validity point of view, because I1, I2 is only one edge, right? You will treat this as lying on both this face and this face, and so you will declare that the object is closed. Some CAD systems have a slightly different process. They actually will find the distance between the two curves, right, on the two respective faces. And if the distance is less than, right, distance between the two curves is less than what is referred to as the same point tolerance. Okay, then they will treat it to be the same curve and drop the other representation. So the same point tolerance is like your definition of zero, right? So if I find the distance between 2 points, and if it is less than this tolerance that you have prescribed, then you treat the 2 points to be the same, right? Now, what do you think this value will be in most CAD systems? What do you think they will be prescribing this value to be? The definition of zero. 10 power minus what? Do you think it will be very high or very low? Some guess. Nobody wants to guess?
Sir, very high, sir.
Well, computers sort of, will take 10 power minus 6 to be their definition of zero, right? For most computations, not for all, okay? they'll take this to be the definition of 0, because you cannot actually check if two values are the same. You cannot do this in a computer very well. All you can do is do this. That's all you can do in a computer, right? Because this will always cause problem, because this will have 10 decimal places, this may have 7 decimal places, and it won't work. It will work only for what is known as integer arithmetic. For real numbers and floats, it does not work. But for CAD systems, the same point tolerance is typically 10 power minus 3. Right? So if you look at the same gap here, and let's say that I have one point which is, the distance between 2 points is 0.001, right? Then here it will take this to be the same point, and therefore you will not have a problem. But if in another system, I have my same point tolerance to be equal to 0.01, and then if I have 2 points with a distance between them to be, let's say, 0.009, right? Then it will take this to be the same point. Why? Because it is less than 0.01, and therefore, it will be okay. Right? But when you take this same object and bring it to a CAD system that takes this to be the same point tolerance, it will not recognize these two to be the same point, and therefore it will treat them as two different curves, and you will have a gap, and it will say that the solid is invalid. And so this remains a big problem, right? While this is a solution that most CAD systems use to avoid the invalidity problem, right? But nevertheless, it remains an inelegant solution, because now you are carrying two representations for the same entity, depending on where you are computing it. If you are computing it on this surface, you use this expression. If you are computing it on this surface, you use that expression. And so that is not a very acceptable or a desirable solution. So that remains a sort of a problem situation for CAD systems. But with a combination of this approach and definition of a tolerance, right? People seem to be managing, except when they ship CAD systems from one system to the other. And if there is a mismatch between these two in the CAD systems, then we have a problem. Right? Okay. So that's pretty much what we wanted to talk about, representation of solids, right? What I want to do next is to talk about a slightly different, design paradigm or design method, right? And this actually came about once the sort of CSG took hold, right? And it became popular, right? A lot of people started using it, but then, people also started seeing that it is very different from works, right? And therefore, they felt that there is a need for a slightly different approach. Okay. Forget the text on the sketch here, on the slide here for a minute, but let me just go back and draw a simple object for you. I'm going to do 2D first, but you can imagine this to be a 3D object. Right? It's a U slot. Now, knowing whatever you have learned so far in your Boolean operations and the CSG construction, you know that this is very easy to construct. So if this is B and this is A union B is my problem, is my object. That seems very easy to do and construct. But here is the catch. What people observed was that designers are not thinking of the object in terms of this operation, where I define a block A and a block B, and I say A minus B. Sorry, this is not A union B, A minus B. Rather, right, they may be interested in a dimension here and a dimension here, and maybe a dimension here. maybe because of some assembly or other requirements, right? These are the dimensions which are critical from the design function point of view. Right, so the designer wants to design this part, scaling or varying these dimensions. Right, that's what is of interest to the designer. Now to go from here to here, the designer has to do some work, right? Because either he has to figure out some of the other dimensions and then add them up to get the dimension of this block, and then do something else to get the dimension of the smaller block, subtract this and this from the overall dimension of this block, and then say that's the size of this block, and so forth. Right? So which means there's a lot of computing and calculation and preparation that the designer needs to do from the shape, the way it has been conceived by the designer, to how the CAD system takes it. And so it is that one CAD modeling solution came up with the idea that we will let the designer design the part in the way that they are thinking about the part. Meaning, if this dimension is important, then that's what the designer will create. So they will create this. If this is what is important, they will create this. And if this is what is important, they'll create this. And then everything else will get connected automatically. And that's the part. And now you can change this, this, or this, and you get a newer part which looks like this. So that was the idea, right? That designers who are actually designing the shapes, not modeling the shape, but designing the shape, they are not thinking in terms of Boolean arithmetic or Boolean algebra. They are thinking in terms of functional elements and the parameters that control that functionality, right? So in some sense, you can think of the D1, D2, D3 as one way that the designer has parameterized the design. Meaning he has decided or she has decided that these are the dimensions that control my design. Whereas here we just have a unit cube or size of the whatever cube that you choose, and that's my parameter, length, breadth, and height. And then length, breadth, and height of the other, and the difference, whatever it gives me, we have to take. Whereas here, the thickness of the prong, the depth of the hole or thickness of the neck, those are the things that are of interest. So this gave rise to this new idea called dimension-driven modeling. And this was the name given by the company that came up with this product. The name of the company was, of course, Parametric Technology Corporation, and the product was, of course, Pro Engineer. Okay, and their idea was very simple: that the designer will construct, right, the part incrementally, meaning that you start with one dimension, so that and then create another one, then create another one, then create another one, and another one. So in this case, these are the dimensions of interest: D1, D2, D3, and D4. So then automatically the others can be finished and the part is done. Right? So the designer does not prescribe the locations of edges and vertices. Designer only prescribes the values of these parameters. Right? So now again, the distinction between construction and storage. Here the construction was by defining these primitives. Now the idea or the point was that the designer will design in terms of these parameters. Okay, D1, D2, D3, and D4. And the system internally then has to calculate all these vertices. Okay, it has to calculate 1, 2, 3, 4, 5, 6, 7, 8 vertices and their connections between them. The fact that these are connected to them. That completes the boundary of this. And to go from here to a solid, basically you will do a sweep or some kind of a extrude operation so that you get a solid. And then from that solid, you can do other changes and get your object of interest. So that was the whole idea behind dimension-driven modeling. Right? Now the advantage was that from here, you go here. Right, through some kind of a sweep operation. Or you can do some fancy sweep or revolve and you can get an object. But the value of this for the designer was that they can now just change the value of D1 and D3 and get a completely different part now. a channel like this and a channel like this, both can come by just prescribing values of this. And that seemed at that time a very attractive option for designers. Designers seemed to like that option because that's how they design. They design a family of parts, and the family of parts are controlled by some select parameters. And that's all they need to do, and they get multiple parts. Whereas here, of course, you can get different designs by changing the size of each of these blocks, right? But then they are not directly connected to these dimensions of interest. Right? And therefore, this became an alternate way of constructing solid models. The representation still remains the BREP, meaning that after all this input is given, you still will have to find the vertices and the edges connecting those vertices. So how does this work then? Right? So the problem that we want to look at now is how does the user define the shape? And from that definition, how do we find the vertices and edges forming the shape? Right? And so this paradigm or this approach by Pro-E basically has these two steps. Right? One is that it gives the dimensions of my geometry, right, by either prescribing a number or some expressions. And then these are solved, the vertices are solved for in sequence. Okay. Now this is important because that is what actually gave a lot of the value to Pro-E, that it could do this very fast. And let me see the next picture and then I can, sorry, what time is it? Okay, just a couple of more minutes. So what I'm just going to, yeah. So I mean, I guess the point that I have mentioned all this while above is what can be referred to as design intent, right? Here, my intent was to control the thickness of the prong and the thickness of the neck. Maybe that was what was of interest to me. Likewise here, right? Maybe the interest is that the size of the box is always in this aspect ratio. The hole always stays in the center, and maybe its size is always fixed. Right? So that's the intent that the designer wants to capture, right? Irrespective of the final shape that he creates or she creates. Right? Now, this is what this whole parametric definition will achieve. Right? That the user will prescribe dimensions. I mean, I'm just showing the final result now, and I'll just show you how the user can achieve this. Right? So you can see the parameters here. D1 is a parameter. D2 is defined in terms of D1 to prescribe the location of the hole in the center. Right? Likewise, D3 is prescribed as D1 by 2 to prescribe the 2:1 to maintain the 2:1 aspect ratio. And D4 is D3 by D2 to again make sure that the hole is in the center. And D5 is 50 to ensure that it is a fixed hole size. Right? So this is something that is prescribed by the user. And the challenge is from this piece of information, given, say, a value for D1, some X, right? The system should be immediately able to calculate the vertices and the edges and the locations of all these points that constitute the boundary of this object. That's the problem. So how do we do that is where the two approaches that we will now study differ. One was promoted by Pro-E and the other one by another company, and we will look at both in the next class. I'll stop here now. Raghu was supposed to come, but he had some issues with power. Kumari, has he been able to resolve it, or he's still out of power?
No, it is still not there.
Okay. Fine. So my request to you would be to wait for about 5 or 10 minutes and then leave, or do you think it's unlikely to come?
Just call me.
Yeah, you can just check. So he was going to introduce SolidWorks to you as a modeling tool, and I think we could not organize the licenses on the laptop yet, but I am hoping that he will be able to do that shortly. So any of you who want to use that can also use that. And I understand that if he's not able to do it today because he has no power at home, he will try to do it on Saturday. He will publish the time with you, and if you are all available, I request you to please concur and have that session with him. Okay, let's just wait. Yeah.
So he still has the power issue.
Okay,
so
fine. So my suggestion would be that you can coordinate with Raghu and find out a time and maybe schedule it with the class so that you can have this session.
Okay. Yeah.
Okay. Yeah. Fine. So you folks can leave now, and then Kumari will be in touch with you for scheduling the lab. Yeah. And Saturday, I suppose we are having the quiz, right?
Yes.
That is confirmed. Yeah. Okay.
Yeah.
Fine.
The timing is not confirmed. So if you have a.
I don't have any preference. I have a meeting in the morning starting at 10, but I can start the quiz anytime 11, 12 or in the afternoon also. So
Okay.
yeah, please confirm the time with Kumari. Yeah.
Yeah. We'll
Okay.
do in the morning. Huh?
Okay, fine. Yeah.
Yeah. Okay.
We can finish it off. Right.
Yeah.
Thanks. Yeah. I will leave now.
Thank you, sir.
Thank you, sir.
Bye,
Thank you.
sir.
Bye.
Thank you, sir.
Bye.